This video is on writing and solving proportions. It's lesson 36 in your book on pages 223 through 229. So where do we use proportions? Proportions are used in reading and drawing maps in architecture and also in construction. So solving problems in this situation requires knowledge of similar figures. Similar figures have the same shape, but they are not necessarily the same size. For example, triangle ABC is similar to triangle EDF. All the angles are the same. They're exactly the same shape, just EDF is a little smaller. We use this little squiggly line to denote similarity. Similar figures have sides and angles that correspond, or kind of go with each other. Corresponding sides and angles are found in the order of the letters in the similarity statement. So, in this case, triangle ABC corresponds to triangle DEF in that A corresponds to D, it's the first letter, angle B corresponds to angle E, it's the second letter, and angle C corresponds to angle F. Corresponding angles of similar figures are congruent. So angle A and angle D are exactly the same. Angle B and angle E are exactly the same, and angle C and angle F are exactly the same. The sides can be congruent, but more often they are proportional, meaning that the side between A and C is proportional to the side between D and F. And same thing for between A and B and D and E, and between B and C and E and F. So AB over DE equals BC over EF equals AC over DF. Their proportions, or their ratios, are exactly the same. Now, a scale factor is the ratio of a side length of a figure to the side length of a similar figure. So if you're looking for the scale factor in these two triangles, you would take the longer side. If you're looking for the scale factor of ABC to DEF, you would divide AB by DE. Now, AB is 2, DE is 1, so 2 over 1 is 2. Now, the scale factor here is 2 over 1, or it can also be written as 2 to 1, meaning that for every 1 unit in the smaller triangle, the larger triangle has 2 units. Here's an example that needs to be in your notebook. This is about finding measures in similar figures. Here we have two similar figures, and we know they're similar because it says PQRS is similar to WXYZ. Now that means that angle P and angle W are congruent, angle Q and angle X are congruent, R and Y are congruent, and then S and Z are congruent. Part A, we need to find the measure of angle Q and the measure of angle W. So we'll start with angle Q. We know angle Q and angle X are congruent. And in this picture here, they tell us that angle X is 80 degrees. So that means that the measure of angle Q is also 80 degrees because the figures are similar, so corresponding angles are equal. We also need to find the measure of angle W. We know that angle W is congruent, or the same as, angle P. And in this larger picture, they tell us angle P is 120 degrees. That means that angle W is 120 degrees. In B, we need to find the scale factor of PQRS to WXYZ. Now that means we need to take a side length in PQRS and divide it by a corresponding side length in WXYZ. So we need to find the sides in each of these figures where we know their lengths. Now, here we have side SR. It's similar to ZY, but notice we don't know what side ZY is. We have PS, that's 3, and PS corresponds to WZ, so there's where we're going to use our scale factor. Now, PQRS is listed first, so we're going to take the side length in PQRS, which is 3, and divide it by the side length, corresponding side length in WXYZ, which is 2. So our scale factor is 3 over 2, or 3 to 2. That means that for every 2 units in the smaller triangle, we have 3 units in the larger triangle. Now we want to use the scale factor to find QR and ZY. Now we know larger triangle is 3, smaller triangle is 2, and we're going to use this to find side QR first. Now side QR, its length is A, and that's in the bigger triangle. So I'm going to set this equal to A over the corresponding side in the smaller triangle. QR corresponds to XY, which is 5. Now notice here we have a proportion which we can easily solve by cross multiplying. 3 times 5 is 15, and it equals 2 times A. Now to solve this, since we're multiplying 2 times A and we want to get rid of the 2, we're going to divide both sides by 2. And that means that A equals 15 over 2, or 7.5. So QR is 7.5. Now we also want to find the measure of ZY. So we still have our scale factor, which is 3 to 2. And we're going to set that equal to ZY is in the smaller triangle, so it's going to need to go in the denominator, because smaller triangle in the denominator here means smaller triangle in the denominator here. And side ZY is labeled as B. Now the side that corresponds to ZY in the larger triangle is side SR, which its measure is 6. So we have 3 over 2 equals 6 over B. Now we have a proportion, and to solve it we will cross multiply. 2 times 6 is 12, and it's equal to 3 times B. Now here to solve for B, since we're multiplying 3 times B, we want to do the opposite and divide. What we do to one side, we have to do to the other, and side B has a measure of 4 units. Here's another example where we're going to use indirect measurement. This again needs to be in your notebook. A radio tower casts a shadow 10 feet long. A woman who is 5.5 feet tall casts a shadow 4 feet long. The triangle drawn with the tower and its shadow is similar to the triangle drawn with the woman and her shadow. How tall is the radio tower? Alright, so we have this triangle here, and we also have this triangle here, and we're told that they are similar. That means that their sides are proportional. So, if we take the vertical side, x, over the horizontal side, 10, it should be equal to the vertical side of this similar triangle, which is 5.5, over the horizontal triangle, or side of the similar triangle, which is 4. Now here is a proportion that we can set up and solve, and then we're trying to find x. How tall is the radio tower? So if I cross multiply, I get 4 times x, or 4x, equals 10 times 5.5. 10 times 5.5, since we're multiplying by 10, we just move that decimal point one place to the right, and that is 55. And then to get x by itself, since here it's being multiplied 4 times x, to get rid of the 4 we're going to divide. And x equals 55 over 4. And in decimal form, that would be 13.75. Now this is a measurement, so we also need units. So notice that it says x is in feet. So the radio tower is 13.75 feet tall. That's a really small radio tower. A scale drawing, here's some more vocabulary for you, is a drawing that reduces or enlarges the dimensions of an object by a constant factor. Every scale drawing has a scale, which is a ratio showing the relationship between a scale drawing or model and the actual object. So, that's kind of like the scale factor that tells us the ratio between the drawing or the model and the actual object. Here's an example that needs to be in your notebook. A desk is designed to have 3 drawers on the right side. In the scaled design drawing, the width of the drawers is 4 centimeters. If the scale of the drawing is 1 centimeter to 7 centimeters, how wide will the actual desk drawers be? Alright, so they give us the scale factor. For every 1 centimeter in the drawing, the real desk will be 4 centimeters. So we have 1 centimeter, which is the drawing, over 7 centimeters, which is the actual desk. And we need to know the width of the drawer if on the drawing it's 4 centimeters. Now my drawing amount was on top in this fraction, so it also needs to be in the numerator in the second fraction. And I need to know how wide the actual drawers will be, so I don't know what that is, so I'm going to write x centimeters. Now I have a proportion here, and I can cross multiply. So I have 1 times x, which is just x, equals 7 times 4. And of course we know that 7 times 4 is 28, and we need units, so centimeters is the unit we're working with here. The actual desk drawers will be 28 centimeters wide. Here's our last example. First, we have a property that talks about the ratios of the perimeter, area, and volume of similar figures. If 2 similar figures have a scale factor of a to b, then the ratio of their perimeters is a to b, because length to length is a straight conversion. The ratio of their areas is a squared to b squared, because you are multiplying units, and the ratio of their volumes is a cubed to b cubed. Now we have an example. It needs to be in your notebook. A dartboard is composed of concentric circles. The radius of the smallest inner circle is 1 inch, and with each consecutive circle, the radius increases by 1 inch. What is the ratio of the circumference of the 2 inner circles to the circumference of the outermost circle? Well, we know that the radius is 1 inch in the smaller circle, and it says that each consecutive circle, the radius increases by 1 inch. So we have 1 inch here, we have 2 inches for this circle, 3 inches for the next circle, 4 inches for the next, and 5 to the next. So the radii are in a ratio of 1 inch to 5 inches. Now we need to know the ratio of their circumference. Now notice it says if 2 similar figures have a scale factor of a to b, or 1 to 5, which ours does, then the ratio of their perimeters is a to b. So circumference is the same as perimeter in a circle. So the ratio of the inner circle to the outermost circle would be 1 to 5. Now, the second circle has a 2 inch radius, so its ratio would be 2 to 5. And what is the ratio of the area of the 2 inner circles to the area of the outermost circle? Now, the ratio of the innermost circle to the outermost is 1 to 5 for the radius. So to find the ratio of their areas, we would actually square their scale factor, because area is 2 units multiplied. So it's a squared over b squared, which is 1 over 25. For the second inner circle, which has a scale factor of 2 to 5, we would square that scale factor to find the ratio of the areas. 2 squared is 4, 5 squared is 25. So the ratio of the second circle to the outermost is 4 to 25.